All right, well, I'm going to go ahead and get started. There we go, that went away. All right, thanks everyone. My name is Spencer McIntyre, and I'm going to be talking about the Windows subsystem for Linux today. All right, so we're going to go over a little bit about me, and then we're going to go over what the Windows subsystem for Linux is, some of the implementation details of how it works, and then the attacker notes. So with this talk, I really want to take the approach of looking at it from two aspects. I want to provide information that would be useful for people that really want to dive deep into the Windows kernel and want to actually know how is it functioning, people that might be interested in exploit development, things of that nature. I also, on the other hand, wanted to give information that would be useful for pen testers. That way, if you run across this in an environment, you know a little bit about it, you know the types of information that are applicable to you. So hopefully when it's done, you'll have that knowledge. Just a little bit about me. My name is Spencer McIntyre. This is my third or fourth time speaking at DerbyCon. I'm really excited to be here. I work at Security in the Research and Innovation Department. We do special projects, internal tool, and vulnerability development. I work on a bunch of open source projects, and I like to do Windows kernel things. So stuff about me. Windows internal, so the subsystem for Linux. So what exactly is it? So it was Microsoft's initiative to allow the native execution of x86 64-bit ELF executables on Windows. So prior to the Windows subsystem for Linux coming out, the only way you could do this would be you'd have to utilize some sort of virtualization technology, and so you'd have to have that layer in between where your ELF executable is running and the Windows kernel. You'd have like Ubuntu or something along those lines. So there's a lot more overhead there, so you have a big performance increase. So the WSL is not virtualization at all, and so because of that, there's a huge performance increase. And what they have claimed is that you get near native execution times of a 64-bit ELF executable as if it were on a full-blown Linux system with comparable hardware capabilities. So the actual functionality is provided by two drivers that we're going to talk a lot more about. There's the LX Core and the LXSS that are going to be these two drivers that are providing this functionality. So this is Microsoft's diagram. I did not create this diagram. This was on their blog, so there's credit down there at the very bottom. I didn't make this. But this is how it actually gets started up. So when you actually go and you run bash.exe, that's a portable executable, and that's going to communicate to the LX session manager. It's a service that's running. That's then going to communicate down into the Windows kernel, and it's going to start up a new instance of the LX session for your particular user. And so that's an important thing to know for an attacker's perspective that we'll get on in a little bit, is that if one user is logged in and they start bash multiple times in multiple CMDs, all of those are sharing the same environment. So those are all interacting. It's only started once per when the user logs in, and so when the last of those bash files that are bash commands that have been run close out, that is when the session is then terminated. So there's one regardless of how many instances of bash that you're running. So those are all shared. And once the LX core starts up its own init process, and that's when the actual ELF executable bash runs, and that's when you have all of your access to like the readline library, your completions, all that native functionality that as Linux users we're used to having inside of our bash environment. So that those two drivers that I just mentioned, the LXSS driver actually is very, very small. There's not a whole lot of functionality in there. The primary thing that it does is it calls the initialization in the LX core. The LX core is much, much larger. I believe size-wise it's approximately 20 times larger. It's where all of the syscalls are implemented. It's where all the files, the file system logic is all implemented. That's all in LX core. LXSS is sort of a driver that sits on top of it though, and when LXSS gets loaded by Windows during the boot process, it calls the initialization in LX core, which starts up the driver object, and that is what is actually maintained. But most of the functionality that you're going to be dealing with that's provided by like the syscalls and things like that are all actually implemented in LX core, the much larger of the two drivers. So there's a couple of different ways that Windows is able to provide this functionality to the Windows users to be able to provide this Linux functionality, and a lot of these are via the system calls that are utilized as well as the file system. Sort of in Linux, everything is not everything, but just about everything is accessible via a file. If you want to get kernel information, there's a file you can read out about that. If you want to know like what addresses a process has, there's a file you can read out about that in like the proc file system. As opposed to Windows, in Windows, everything is an object, and those objects are then accessed by the Win32 API that Microsoft has exposed. So it's a pretty different architecture. So we're going to talk about the syscalls that are actually supported by Microsoft to allow these executables to interact with the kernel as well as the file systems. But within the context of each one of the Linux processes that are running, these are not full-blown native Windows processes. These are actually what are referred to as Pico processes. Pico processes are very lightweight, small container processes. They've actually been around for a while. They were done as and created as part of Microsoft's Project Drawbridge, which intended to create the capability for Microsoft to, in the future, utilize other sorts of technologies. I've looked into it, and I cannot find another practical application of where Pico processes are used. To my knowledge, the WSL system is the only place that Pico processes are actually used. But they are the container processes that do not have all of the overhead of a Windows process. And the reason why is because these Linux processes that are running, they don't need to have NTDLL available. They're not going to be making any of the Windows system calls. They don't have any of that. So this Pico process is also limiting what an attacker can actually see about a Linux process from within the Windows environment and vice versa. So like I mentioned, one of the important things is that there's no PEB, TEB, NTDLL. In addition to that, the shared region of the user32, the shared region that's mapped between the kernel and the processes that people that are familiar with kernel exploitation are used to utilizing, that region also is not mapped. So it's not available because the Linux processes presumably are not going to be utilizing it. No legitimate Linux process is going to expect to be able to access the handle table information from Windows. And the Windows kernel does still provide the scheduling functionality, the memory management, things like that. But the rest of the process, it's basically the Pico process is a hollow process. So the Pico processes also get a separate syscall dispatcher. There is an additional syscall dispatcher. There's exactly one that is available on the system. And when that LXSS driver and the LX core drivers are loaded, they register themselves as a Pico process syscall dispatcher. So they're a provider, meaning that when the Pico processes are actually started and the transition is made into kernel land because one of those Linux processes is making a system call, Windows knows that this is a Pico process, so it's going to route that system call to the provider that has registered itself as the driver. In this case, it's going to be LX Core. So these system calls are the primary way by which all the Linux processes are going to be able to interact with the host operating system that is going to be Windows. There is no Linux kernel, strictly speaking, inside of Windows. Microsoft has claimed that it's a completely clean room implementation, meaning that all of the system calls that they support were written by them by looking at the man pages, ensuring that the prototypes are all set up and things like that. So there's a couple of variations that we'll talk about in the attacker section for fingerprinting, but it was supposed to be a clean room implementation, so there's no Linux kernel that is technically running. It just appears that way, and it's exposed via these system calls. So when I did my analysis, one of the things I wanted to do is I wanted to know what all system calls were actually supported, because this is going to be one of the attack surfaces that someone running inside of the Linux container would have into the Windows environment. So at the time that I did this on this build 14.385, I compared the kernel that claimed to be running, the version of that kernel, to the number of system calls that were in the Linux kernel source tree for that. There were about 63% coverage of all the syscalls that version of the Linux kernel supported. About 63% were offered by Microsoft and exposed to these binaries. Some of the ones that were missing were actually some of the 32-bit equivalents. I didn't really know this. I'm not much of a Linux kernel guy, but actually the 32-bit equivalents are the newer versions. A lot of some of the older system calls on Linux are 16-bit. Some of the newer 32-bit equivalents are some of the ones that are actually missing. Presumably, Microsoft is still catching up, and they need to support more of these syscalls. So as they continue to work on and improve the WSL, this is probably going to be one of the areas where we're going to see that the gap of that coverage shrink as they start to add in more. Okay, so like I mentioned, when a Linux process is running, it's going to be this Pico process, and when it needs to communicate something to the kernel, for example, it needs to open a file, create a socket, anything along those lines, it's going to have to do that via system call. And so it's going to use its own ABI, and it's going to make that transition into the kernel land. And when the kernel is past the context, it's going to recognize the fact that it is coming from, the request is coming from a Pico process, and it's going to route that to the appropriate driver, and that's going to be that LX core driver. The syscall convention that is utilized by Linux binaries, they follow the system v ABI, which is a slightly different calling convention than what Microsoft uses. Because there is no translation between this, it is actually the responsibility of the Pico system call dispatcher to parse, or not parse, but utilize all the arguments in the native representation. So it doesn't matter the calling convention, which is very important and instrumental in not having to change the Linux binaries, because they are expecting to be able to make the system calls in the native Linux convention, which is different than the Microsoft ones. So the calling convention is slightly different. For Linux, they utilize 6 of the registers as opposed to 4, but it's much more akin to a fast call convention if you're used to 32-bit. The remainder of the arguments are stored on the stack. This is important, so if you are going through and you're debugging one of the system calls, you need to remember that even though you're in WinDebugger, that the calling convention was actually from the system v ABI, not from Microsoft's calling convention. All right, so moving beyond the system calls, there are the file systems that Microsoft has exposed to these Linux binaries. So there are 2 main file systems that are utilized. One is the root file system, where you have your etc directory, your user's home directory, all of that information. The second is the drive file system, which is how the Linux processes can access all of the root of the Windows drive. So in your drive file system, you're going to have your C drive, and everything beyond that you're going to be able to have accessible from the Linux processes. So there's a couple of other, the standard process, file systems is the proc and the sys file system, so you can get basic information if you needed to find like the memory maps and things like that. But these are the 2 primary file systems that allow access to be able to read files off of it. One of the things I found very interesting through this implementation is that because the Linux binaries that are running have access to the full root of the drive, barring any permission issues that we'll talk about in the attacker section, Linux has access to read all of the files off of the root file system. The reverse is not entirely correct. You're not, according to Microsoft's documentation, you're not able to read the files in like the etc directory or anything like that. So presumably antivirus would not be able to scan that, which is kind of interesting because you could potentially hide a file within the Linux file systems. Now that's according to the documentation. I did, however, find a small discrepancy, and that's because within the Windows user that is running the WSL environment, within their home directory and their app data, some of the Linux files that are created do exist there. So strictly speaking from the Microsoft documentation, I don't know why that discrepancy is there, but I wanted to point it out. Assume you've seen that too. You're not in log. Excellent. There we go. I'm not crazy. Let it be known. All right, so the drive file system, despite being root, if you are starting up your WSL environment and you elevate yourself into root, one of the first things to think of is like, oh, like let's just drop an MOF file and we'll get system access and we'll be able to break out of the Windows environment. Wouldn't that be great? Unfortunately, it doesn't work that way. And the reason why it doesn't work that way is that one of the things I'm really going to be harping on throughout the remainder of this presentation is root really doesn't mean anything in the WSL context. It doesn't get you anything. When you elevate yourself from sudo into to root level access, the token that is the permissions of your Pico process, those don't change. And so when you are making your system calls, a lot of the system calls are actually provided by Windows when there's an applicable one that can be utilized versus some of the other ones that can't and are then fulfilled by the Linux core. I forgot to mention that. But the system calls that are actually implemented by Windows utilizing the existing infrastructure, those are still going to utilize the native token and things like that. So when you elevate yourself to root, that token doesn't change. It really doesn't mean anything to the greater Windows host operating system. It's strictly within your WSL environment. You can like read and access the shadow file, and that's great for you. But unfortunately, that's not even shared within other users' WSL environments. So elevating yourself to root, not really going to be the best way to do anything. All right, so this is just a real quick demonstration of showing that. So this could potentially be a hiccup for users that aren't necessarily used to working in this type of environment. So if you're in the WSL environment and you have a sensitive file and you want to protect it, maybe you would mark it as owned by root and only readable by root, but truly not going to do a whole lot for you. So in this case, we're putting a super secret onto a secret text file. We're chomodding it, and we're taking a look and making sure the chomod command actually did execute successfully. But then when we take a look at it, the file permissions are still 777. So might be a hiccup for some users. So point being, if you're a pen tester, it would probably be a little bit advantageous to look for file permissions within the drive FS, because you may get lucky. So that kind of takes us right into our attacker notes. I'm going a little bit quickly here. I'm trying to manage my time appropriately. So one of the first things that you'd probably want to do is, like, if you're an attacker, you're a pen tester, and you're in a Windows environment, you know they're running Windows 10, maybe they have WSL, you'd want to be able to identify, am I in WSL? I went into this thinking it'd probably be really difficult. Turns out it's actually ridiculously easy. You can pretty easily identify that the Linux session that you're on is actually Windows. So I have a couple of obvious ones, and I want to break these out into obvious and behavioral, because if Microsoft were to change them, they're probably going to change the obvious ones. My personal opinion and experience, they're less likely to change the behavioral ones, but within the obvious ones, there's actually, it says Microsoft in the proc version. I highly doubt any legitimate Ubuntu distribution is going to actually have Microsoft in there. You can also check for the drives mounted in the /mount directory. So like I said, that drive FS is going to have /mount/C, /mount/D if you have a D drive, things like that. So if you're looking in there, you're probably going to have those drives. Some more interesting ones would be some of the behavioral clues. So there's exactly one module that gets loaded up into the sys modules, which seems kind of a little bit sketchy from a normal Linux user's perspective, is that you know that you're probably going to have a few loaded kernel modules running. You need to have drivers, anything like that. I'm running Fedora on my system. I need to have like a wireless driver, a graphics display driver. There's a number of drivers that are loaded on my system. To be in an environment where it claims that only one kernel module is loaded, it's pretty indicative that something is going wrong. In the proc file system that exposes information regarding the running processes, there are missing fields that are entirely implemented. This could change by Microsoft as they improve their support. They're probably going to expand on the proc file system, so that'll probably change as well. Another one that I found very interesting, this last one is actually my favorite. I ran across this while I was testing one of the Metasploit payloads, and that's actually the checks on the mmap system call are actually much more strict. So in that third argument where you're supposed to specify some of the flags, on Linux, you can specify any of the flags that are defined, and if you specify additional flags that are undefined, it just ignores them. They don't do anything. On Windows, however, if you specify a flag that is undefined to the mmap system call, it will return an error. So you can have the exact same function with this extra 0x1000 that's an undefined flag, and that'll run successfully on Linux, but on Windows, it'll return an error. So that's kind of an interesting behavioral clue, and that's actually because of the implementation that Microsoft used for that system call. So, like I mentioned, I found that while I was looking through some of the Metasploit payloads. So another thing that I assumed a lot of pen testers would be very interested in is, like, if I'm looking at a WSL environment, what payload options do I have? Which ones of these are going to work? So up here in the right are going to be the payloads that I actually tried and which one of them were successful. So there was the brand new Metal payload. I don't know if anybody follows the Metasploit development, but it's a really cool payload that is like the future of the Linux interpreter system. That one unfortunately did not work, and the reason why was exactly because of this mmap system call. They may be changing it in the future version, but because Metasploit has a preference towards wanting to keep the shellcode much smaller, it would expand the size out a little bit more to clean up the arguments. So it was just kind of a fluke that was found, but it actually is in that particular stage, or that why that payload was not working. The unstaged shell reverse TCP worked correctly. The x86 interpreter reverse TCP does not. And that's because it's the x86 version. Microsoft, the WSL project is intended to run 64-bit binaries, and because of that, 32-bit ELF executables are not supported. You can't run a 32-bit ELF executable in WSL at this point. On normal full-blown Linux distributions, you can run 32-bit binaries. Like I could run a x86 interpreter on my Fedora system. Please don't do that, but you could do that. On WSL, it's very much focused on like just the 64-bit. And last but not least, my personal favorite, the Python interpreter does work. Fully featured for the most part. Slight caveat to that, but you get your session back. You can interact with it. You can run commands. That's presumably because the installation of Python that's included in the Linux standard base is present in the WSL environment, so you can utilize the Python interpreter. I say that it is mostly supported, and that's because at the time of my testing, I believe this is probably another one of the things that Microsoft is going to eventually change very soon, is the ifconfig command was not entirely supported. You would get errors out of that. And so retrieving IP addresses and things like that, utilizing the functionality that the Python interpreter actually does it by interacting with those files that expose the information through the kernel, that information was not entirely available. So you'll have trouble if you're trying to retrieve the IP address using like the ifconfig command. But most of everything else worked well. You could get a shell, you could upload and download files, believe you could route through it. So all that good stuff. Additionally, might be interested in what the Linux kernel protections are available, since we know that there's not a Linux kernel actually running in there. So what types of protections are actually provided by the Linux kernel? You have things like data execution prevention or DEP. You have ASLR, null page mapping, and things like that. I tested all three of these, the very basic implementations, and they are all implemented. Specifically, when it comes to ASLR, I believe the reason why this one was actually implemented is because the functions necessary to allocate the memory are some of the functions that are already available in the Windows API. So the system call in LX core is not fulfilling it itself. It's forwarding those on to the Windows implementation. So all the features and functionality that's actually there is being leveraged. Okay, so cross-process access. So if you are in a Linux process, what can you get from a Windows process, and vice versa? These would be the types of things if you need to break out of the environment. So from a Linux process, you can't access the Windows processes. This is unfortunate because Windows, once again, provides access to those processes as objects that are accessible through the Win32 API that you can't access from the Linux environment. Windows, however, can list Linux processes. So if you load it up in Proc Explorer, you'll see a bunch of Linux processes, your bin bash, your Python, all those things are all listed out as child processes of the init process. The PIDs do not match up. As you would expect, the lower number PIDs are in the Linux environment, so those process identifiers don't match up from what you're seeing in the Windows environment. One of the things that you actually can do is you can access the from Windows, you can access, I think I'm a slide ahead here actually. Yeah, so I covered on all that. I'm going to run behind a little bit. From Windows into Linux, so you can access very minimal amount of information. So Windows allows access to the processes via Win32 API because they're objects, like I just mentioned. So the way you do that is actually utilizing the open process function, and you pass it in the different arguments that provide the level of access that you need to it. According to the Microsoft documentation, you're not supposed to be able to use the process query limited information. However, when I did it in my testing, I was able to use the process query limited information to get basic information about the Pico process. Because it is a Pico process, though, you cannot do things like open it with the ability to read and write memory. You can't create a thread. You can't do all those things that you could for a normal full Windows managed process. What you can do is you can query limited information, which basically allows you to check the exit code when the process exits, and you can call it with synchronized, meaning that you can wait for that process to exit. So this is slightly interesting because, as us Linux users know, in Linux, the exit codes of processes is actually somewhat important. There's a standard list of exit codes that mean different things. So from the Windows environment, you could find a running process, theoretically wait for it to exit, and extract information out of that for you. So you could get the information out. It's the low 8 bits of the Windows status code correspond, or excuse me, it's the second byte that allows you just have to do a bit shift over 8 times, and you can get that the exit code from the Linux process. All right, like I mentioned, the cross-user access. So if you have multiple users running within the WSL environments, those are specific to each one of the users, so you can't actually access each other's files. The file systems are independent. When I checked this, actually, when one user starts it up, it has to download a large amount of data from Microsoft to have all like the Linux files and everything. And when you go over to another user, despite the fact that one user had already done that, they have to download it all as well. So those file systems are independent. Unfortunately, if you get root level access within one WSL environment, you're not going to be able to extract like the other user shadow file. And that is me time saying that I am up. I think that's just about it. Oh, there's my closing thoughts. So like I said, root really doesn't mean anything. Some of these nuances are probably going to trip up new users. So I got this really sweet desktop because I signed up for the Windows Insider program in order to be able to test all of this. So cool, Ninja Cat. And Those are all my references. Thank you, everyone.